Okay, next up is what's called the equivalent annual interest rate, or EAIR. In some textbooks, it's called EAR. Okay, so EAIR stands for equivalent annual interest rate here. And that's going to be important to us because in the real world, oftentimes we're going to have to compare a project with X% interest compound annually with another project that is Y% interest compounded quarterly or compounded monthly or whatever. So that's clearly apples and oranges, and we need to have a way to look at them both on a level playing field. And EAIR is what lets us do this, okay? And so let's get all pedantic on this now and get the definition. So the equivalent annual interest rate is the interest generated per dollar over a year, irrespective of compounding period. That's awesome because now we can put everything on the same footing. Doesn't matter if it's monthly, quarterly, whatever, we can put them all on an equivalent annual basis and compare and contrast them. And not only that, but we have a simple formula to get the equivalent annual interest rate from any old interest rate with any old compounding period. Here's how it works. Equivalent annual interest rate is equal to 1 plus our native R, so that would be like 6% compounded quarterly or whatever, raised to the number of compounding periods per year minus 1. And again, R is that native interest rate. Okay, so let's do a couple of examples here. So how about 10% compounded annually? What's the EAIR? Okay, well, it's going to be 1 plus our native R, which is 10%, okay, raised to the 1 minus 1, and that's equal to 10%. You should verify that, but that's what it is. Okay, so now how about 10% compounded quarterly? Okay, let's bring our Excel back in for this. Okay, so the EAIR is equal to 1 plus 10%. Now it's compounded quarterly, so that means there's 4 compounding periods in a year, and that's going to be minus 1. Okay, and let's just compute that in Excel. All right, and that's 0.4641, commonly known as 46.4%. So that's pretty amazing. So the interesting thing about this is exactly the Big Shark situation. So comparing the Big Shark deal to the prior lender's deal, the prior lender had 10% interest compounded annually, and Big Shark has 46.4% interest compounded annually, right? So that is really usurious. I believe that there are laws against that for consumer loans kick in around 33%, meaning that any interest rate charged above that is called usurious and illegal. So that would be illegal. Okay, one more thing about compounding periods. We have to understand this thing called the nominal APR. Nominal APR stands for nominal percentage rate, or nominal annual percentage rate. So it'll be called nominal APR or APR, and we need to know how it's defined. So the nominal APR is just equal to our native interest rate R times the number of compounding periods per year. So what do we need to remember about this? Nominal APR is a universally agreed upon term. It always is defined by this equation where the little r here is our native interest rate, okay? And the bad news is that when you see just APR out there in the big bad world without the nominal in front of it, to some folks that means nominal APR, and to other folks it means EAIR. So that's bad news, right? So we want to be careful. So our convention is always going to be that whenever we see APR, we mean nominal APR, right? All right, so let's look at some use case examples for this. So let's say we have our native interest rate of R% compounded annually, okay? Then in terms of APR, we would say here, the APR is equal to 7% times 1, or 7%. And if we were discussing it with anyone verbally, we'd say that nominal APR of this project is 7% with annual compounding, which happens to be, in that case, the same as the native rate. All right, so let's look at one that is a little more meaningful. Let's say we have a native interest rate with quarterly compounding. So we have R equals 10% compounded quarterly. That's our native rate. So using our definition of APR, it's just what's the APR? The APR is the native rate times the number of compounding periods per year, 10% times 4, or 40%. And so we'd say, talking about this verbally, for this project, the nominal APR is 40% with quarterly compounding. Okay, and what that means is, of course, we can get back to our native rate of 10% by just dividing by the number of quarterly compounding periods per year. So bad news about APR. It's very common, but it's usually not helpful. It doesn't capture the awesome power of compounding, which again, almost every contract in the world has compounding, except for a couple of exceptions in things like real estate construction, etc. And it almost always underestimates the equivalent annual interest rate, which is the word and the light and the way, evaluating everything with units of years. So that's not so great. So why is APR, nominal APR, even around? It's a long story involving the finance industry lobby. Because it usually underestimates EAIR, they can advertise loans with the nominal APR, and it looks to you like you're actually paying less compound interest than you actually are. This is exactly the type of thing that Elizabeth Warren tried for years to get rid of, and we'll see, depending on what happens with the 2020 presidential election, who wins and who gets appointed to what, to see if maybe there will be some changes made there. But anyway, APR is not going to go away no matter what. There might be more disclosures required about what APR means and to additionally always state the EAIR, something like that. But we'll see. We'll wait and see. Okay, so to make the APR useful, right, because it's not useful, EIAR is very useful. So we're going to want to divide it by the number of compounding periods per year, and that gives us our native interest rate, R. And then once we've got our native interest rate, R, what are we going to do? We're going to convert that to the equivalent annual interest rate. So it's a two-step process, right? Drop the APR down to R, the native R, and then convert the native R to the equivalent annual interest rate. Okay, so that's going to be our step 2, is compute that equivalent annual interest rate. Okay, so what are some examples here? We've got, after we convert to R, we get 6% compounded monthly, 2% compounded quarterly, etc. All right, so let's do an example here. So we're going to need APR and EAIR for this example, and here's why. We're evaluating money market offers by 2 banks. Bank 1 is offering 5% compounded annually. Okay, so this is, let's just note this right away, it's the equivalent annual interest rate, right? It's what we've got in time equal year terms, and compounding matches that in years, so that's our EAIR. Okay, so Bank 2 has 4.5% APR with monthly compounding. So what we want to do for this one is get the equivalent annual interest rate so we can compare it to Bank 1. So the EIAR for Bank 1 is equal to 5.0%, as we just said. Okay. All right. And for Bank 2, we have the, let's bring our Excel back into the act again here. Okay, so for Bank 2, the R is going to be equal to 4.5%. And how many compounding periods were there per year? That was compounded monthly. So that's going to be divided by 12. Okay, and so that's going to be equal to 0.0035 or 0.375% interest rate. So that's our native R. So our EAIR now is we just plug in that native interest rate, 1 plus, let's say this guy, okay, how many compounding periods per year? 12 minus 1. All right, so let's take that and go ahead and compute the answer, and we get 4.594%. So now we've got two things we can compare on an apples to apples basis, right? Equivalent annual interest rate for Bank 1 is simply the native interest rate, 5%. Equivalent annual interest rate for Bank 2 is less, okay? So Bank 1 offers us a better deal. And what's another way to think about? Bank 1 is going to build you a bigger pile of money per year than Bank 2. Okay, some more thoughts on this. In our time value formulas, always want to use our native rate R with our time measured in consistent units. We can also use, whenever we want instead, we could use our equivalent annual interest rate with time measured in years. Either one is going to be fine. What is not going to work is APR. If we put APR in our future value, present value formula, it's just going to be wrong because, again, APR is sort of a meaningless quantity, sadly to say, even though it's very prevalent in the consumer loan world. Okay, so this is going to work for our fundamental discounting equation, the future value, present value formula, all those equations. Okay, so now let's take a look at a very important application of APR and EAIR, and that's bonds. Okay, so most corporate bonds and treasury bonds, first of all, are not what we call amortizing loans. Amortizing debt instruments, how's that? Amortizing instruments are instruments where every time the borrower makes a repayment, they're repaying back some of the principal, some of the amount that was originally borrowed, and they're paying interest on the balance that hasn't been paid back yet. We'll get to amortizing loans soon, but for most corporates and treasuries, the instruments are not amortizing. Like mortgages are a good example of amortizing loans. We'll get to them in the next chapter. But also what we're most concerned with right now is that they pay interest semi-annually. All right, so we're going to have to deal with that. So let's get some terms under our belt here. Most corporate and treasury bonds are characterized with these definitions. So principal is just the amount borrowed per bond, the principal amount borrowed per bond. And you just got to memorize these. I'm sorry to say, but it's true. See a definition, memorize the definition, right? Okay, so what else do we need to know? Face value is the principal to be repaid at the end of the contract, and it's also sometimes called par value. And we're going to assume, which is true for non-amortizing bonds, that principal equal face value equal par value. Okay. So the amount originally borrowed is the amount to be paid back. The coupon is defined to be the total amount of interest paid per bond, and that's measured in dollars. So the coupon is a dollar amount, or thousands of dollars, of course, or millions of dollars, but the units are dollars. It's not a percent type thing. Okay, and so it's the total amount paid per bond per year, and we need to know, this is very important, half of it is paid every 6 months. So this is going to bring in the APR problem, okay? And the coupon rate of a bond is just equal to the coupon, that total for the whole year divided by face value. And once we do that, we have dollars divided by dollars, and that will be reported as a percent. So we need to think about bonds in two cases. First one is at issuance, and then the second is just going to be flapping around trading in the marketplace after the bond has been issued. Okay, so we're going to assume that all our bonds are issued at face value. It's a pretty good approximation. It makes our life much simpler, which I'm always for whenever we can do it. Okay, so the at issuance, the APR for the bond is equal to the coupon rate. So it's described as X% interest compounded semi-annually. All right, so now to compare various bonds. Remember, you can't compare APRs, it's just hopeless. So we're going to have to find the EIAR of all the bonds we're looking at to compare them, okay? And the EIAR in bond world is called yield to maturity, or YTM. So whenever you hear a bond person talking about YTM or yield to maturity, they just mean equivalent annual interest rate. All right, so let's do an example. So let's look at Simpleco. It's issuing a 7-year bond with $1,000 face value. So that's the original amount that's going to be given to them to bond and repaid at the end, right? And they've got a 10% coupon rate, okay? So let's find out the APR of this bond, and let's find out the R in, that's going to be in native 6-month units, right? Because the coupon's paid every 6 months. We want to measure time in 6 months, right? So we'll have to get our native R in 6-month time periods. And then let's get what they call in bond land yield to maturity, which we know is just the EAIR, right? And these are our 3 steps. We have an APR, get the R, get from that the EAIR, all right? So we want to do this, of course, for a purchaser of the bond at issuance, okay? All right, so the APR of the bond is equal to the coupon rate, okay? And how do we have to describe that? Because it's paid twice a year, it's the coupon rate, so we say 10%, right? Compounded semi-annually, okay? And you can read the gray information down here to see how the coupon rate was actually figured out when the initial bond contract was established. But again, that's in gray, so you don't have to do that if you don't want to, okay? And now we have the APR, we can get the R. The R, the native interest rate, is always from our formula definition of APR, right? It's just the APR divided by the number of compounding periods per year, right? So that's going to be 10% divided by 2 periods per year equals 5%. Okay, Yahoo. And you can tell, some of you, that I'm an aging wasp who can't do math very well in my head, so I keep the numbers simple in these examples because I can do the simple numbers in my head. Okay, so let's see what we got here. Now we've got the R, we can get the EAIR, right? Okay, so it's just 1 plus, we just plug in the EIAR formula, right? To the 2 minus 1 here. So it's 1 plus our native R, quantity raised to the number of periods per year, minus 1. Okay, and let's go ahead, give myself a little space here. Let's go ahead and calculate that. Okay, blammo. So we get 0.1025, which in percent terms is 10.25%. Okay, and you can see it's true, it's really true, it's 10.25%. So look at this, the coupon rate is not telling us what we're really going to be earning in terms of interest from this bond because of the awesomeness of compounding, okay? So that's why coupon rate, APR, are not very useful because they really don't tell us about how much interest we'll be earning or paying if we're the borrower. Second situation we have to think about for bonds is bonds after issuance, right? So after issuance, right, the price of the bond is determined by the marketplace, right? If we're thinking of purchasing it today, it's whatever the marketplace has decided that bond is. We saw that in the chapter 1 with the HCP bond, right? The price of that bond went down well below face value because of the panic of the moment. These days, a lot of bonds are trading at higher than face value because interest rates are so low across the board these days. Okay, so the purchase price is not in general going to be equal to principal or face value. All right, so now for this type of situation, the coupon rate is mainly just used to determine the dollar amounts of interest paid every 6 months, okay? And now finding our native interest rate is a much more significant problem, okay? We're gonna have to do this based on the current bond price and the contract stipulations, and we are almost always going to need to draw a cash flow diagram to make this work for us, okay? And once we find the R, we can find our yield to maturity from our usual EAIR formula. Remember, yield to maturity, same thing as EAIR, okay? So our steps are going to be, number one, we want to get that native interest rate, and that's going to come from just looking at the contract, seeing what cash flows we're going to get when, and writing down, using the fundamental discounting equation, writing down the right equation, solving it for R, all that jazz, and then we get the EAIR from that. Okay, so let's do an example to show you what I mean by all this. Okay, so let's say on the first day of 20X1, SimpleCo issued a bond maturing on the first day of 20X7, okay, with $1,000 face value, so $1,000 borrowed for each bond, $1,000 to be paid back, and a 10% coupon rate. So 10% coupon rate, we know that was the APR at issue, like that. Okay, and so today it is January 2nd, 2000X6, and the bond is trading at 950. So a coupon payment has just been paid, okay? So a coupon was paid yesterday. Okay, so if it was maturing on the first day of the year, we know that all of the coupon payments and the final amount of face value, principal, par value to be paid back is going to happen on the first day. Okay, and we're at the second day, so a coupon was paid yesterday. All right, so we want to find R, we want to find our yield to maturity, which is equal to our EAIR, okay? And that would be, of course, for a purchaser of this bond today with the price here at 950. So let's see if we can figure it out. So I think first thing is going to have to be cash flow diagrams, okay? If we're doing cash flow diagram, we got to know what our cash flows are going to be. So how much do we get every 6 months, right? So it's going to be the coupon over 2, all right? So let's think about this a little bit. $1,000 face value with a 10% coupon rate. That means that the coupon is 10% of this, or $100, and that's going to be paid every 6 months. 50% of that is going to be paid every 6 months. Okay, so that's going to be equal to 100 divided by 2, and that's equal to 50 in most circles. All right, now for a cash flow diagram and why we have to do it. Why is it important? Let's go ahead and draw this, and let's put some times in here. Okay, so we've got 0 here, and we've got 1 here, and we've got 2 here, and this is going to be, let's do time measured in semi-annual periods. Okay, so at t equals 0, what are we gonna do here? We're going to pay 950. So we're doing this cash flow diagram from our perspective, right? And then in semi-annual period, we're going to get 50, come on fella, here we go. We're going to get $50 in 6 months. Okay, and we'll just pull that over there. Okay, and then at the end of 2 semi-annual periods, we're going to get another $50, but now the principal amount is going to be paid back also, and that's 1,000. So let's just move these into place here. All right, and let's label everything. So we're going to get, so we get the final interest payment, and the full amount borrowed long before we came on the scene has to be paid back. And so this is going to be 50. All right, so there it is. There's our cash flow diagram. I think it's kind of hard to assess this out without drawing that diagram. Okay, so there is our cash flow diagram. And yeah, let's think about what this means. This means that as always, this 950 is made up of two tranches, right? One that's going to grow into 50 in one period, and another tranche that is going to grow into that whole mess in two periods. So let's just fill that in. So it's got to grow at R%. R% is what we don't know, right? Into 50 here in 6 months. Okay, and another portion that is going to grow into 1050 in 1 year. All right, so let's see if we can write an equation to figure this out. And the way that we're going to do this is use our fundamental discounting formula, which is all the way back here somewhere. Here it is, okay? So that's the equation we're going to need to use, and we just apply it to the situation in this cash flow diagram. So we have our 950 is equal to 50 divided by 1 plus r to the 1 plus 1050 divided by 1 plus r to the 2. Okay, and if you work that out, you get 7.796%. Okay, so use to find this trial error goal seek in Excel, or we could use, in this case, the quadratic equation. Okay, and at the end of this lecture, for those of you who want to see it, I'll show you how to do this using goal seek in Excel. But for right now, just believe me, you can try on your calculator, take you not long at all to verify that if you plug in 7.796% into this equation, you do get 950. Okay, so enough of that. Let's go ahead and get the EAIR. Okay, so that's equal to 1 plus 7.796% raised to the 2 compounding periods per year minus 1. Okay, and I'm not going to throw that into Excel. What the heck? I will throw it into Excel just to confirm for us all that there are no typos there. Okay, and I get 16.2% as shown right here. So that would be a pretty nice deal if we were confident that there was not going to be any bankruptcy or anything like that along the way. Okay, another thing that this is in gray, so you don't need to know. In the 1980s and 1990s, continuous compounding was popular. It's not so popular anymore. It is used actually by a lot of quants because you have this continuous set of equations that makes differentiation and integration a little easier. But for us mere mortals, we don't have to worry about that. Okay, and that's it for this chapter. So for those of you who are eager to cut out and do something else, that's a big mistake because all your time should be spent on finance, but whatever, it's fine. And for the rest of you who want to see how to compute this R in GoalSeek, let's do that right now. So for those of you tuning out, see you soon. And for everybody else, hold on and let's go ahead and do this. Okay, so Control A, Control C, let's bring it back into Excel here. And I'm just gonna wipe out everything so we have a little room to work here. Okay, and I'm gonna say 950 is equal to, go ahead and do that. And to find this in Excel, I want to use a cell reference. So what I'm going to do is I'm going to put a guess up here in, you can't quite see this, so let me do that. So I'm going to put a guess up here in C3 of, I don't know, 10%. It could be anything. And also, bear with me for a second, I'm going to show some more decimal places there. Okay, So, and what I've got to do down here, actually I'll bring this up here. Okay. I'm going to have something like this, and let me again, let's bring this down so you can see better what I'm doing. So I'm going to turn this into a formula that Excel can work with, and I'm just going to say C3. So that's going to be 1 plus C3, and I'm going to do that again here, C3, okay. And when R is equal to 10%, PV tote equals that. When R is equal to 5%, we're up to 1,000. So 5 is too small, and 10 was too big, and that's all good and fine, but I am too lazy to do this over and over and over again iteratively, so I'm going to have Excel do it for me. So we want PV tote. We want to find the R that gives us the PV tote of 950 here. So I'm going to go ahead and say data, what if analysis, goal seek, and I want to set cell C4 to the value of 950 by changing cell C3, and I'm going to say blammo. Okay, and I get the exact same answer that I had before, 7.796%. So that's a great way to do that. You can also solve equations like this, where you have integer exponents here, and they only go up to 2. You can use the quadratic equation. The way you would do that would be to use the magic of algebra on this, multiply both sides by 1 plus r squared. So then you would have 950 times 1 plus r squared. Okay, and what else do we have here? We would have, I need 950. Okay, that's good. Okay, and that's going to be equal to 50 times 1 plus r and plus 1050. All right, and that you can see with a little bit of work is something that very well matches what we all know and love or hate and hopefully remember from high school algebra. Ax squared plus bx plus c equals 0. So you just plug into the quadratic formula, and that's going to give you 1 plus r. So you subtract 1 from that and get the same answer. Okay, so that is it for now. If I don't see you in office hours or the discussion forums, I'll look forward to catching up with you soon in the next video.